So, some announcements. On Thursday, the next set of, the worksheets and homework worksheets 2 through 5 and homework number 3 are due. That's the 6th. We will also be having exam number 3. It's 60 questions. You get 1 sheet of notes. It'll be just like the previous ones on Scantron. You need to be here for that. Now there will not be class on Tuesday next week. It's a holiday. It's Veterans Day and City Colleges is closed. So just letting you know, not gonna be here on Tuesday. But we will have class on Thursday that week on the 13th. Additionally, considering where we're at, worksheets 6 through 9 will be due on the 2nd. Homework number 4 will be due on the 2nd, and your presentations and papers will be due on the 4th. And I will get up a schedule for the presentations up by the end of the week. I'm just going to randomize the order of people in the class, put it up as a schedule. The presentations will start on the 4th. Any questions? Question? No? Yes. Yes. Oh yeah, make sure your topic's been accepted. I think everyone in this class who submitted had it accepted. If you have a point on your grade, then it's accepted. Yeah.
Would we be able to resubmit the topic somehow?
Yeah, you can just submit again.
Oh, because I don't think I was able to do it the first time, so I don't think there is a topic there.
Then you should just be able to submit to the assignment. You do have to submit a file of some
Oh,
sort.
no, I thought it closes.
No, it doesn't close. It's still open. That's how you can always submit late work. All of the assignments are left open. So the topic assignment is still open, so you can always still submit. So if you haven't submitted your topic, please do. I'll just see it as late, but you'll get your points. Yeah. So, continuing on with chapter 7, mountain building. Let's talk about mountain building. So mountain building has occurred during the relatively recent geologic past. Some examples are the American Cordillera, which is on the west coast, the Alpine Himalaya chain, and the mountainous terrains of the Western Pacific. So the western side of the Pacific Ocean, there's lots of mountainous terrain there. So mountain building can happen in a few different ways. So here are some reasons. The North American Cordillera and the Andes Mountain are these young mountain belts here along the west coast of North and South America, the Alps and the Himalayas, and then there's the Western Pacific. So the red areas are the young mountain belts that are less than 100 million years old. The purple areas, like the Appalachians, the Caledonian, and the Urals and such, are old mountain belts. Shields are big areas of exposed bedrock and stable platforms. The gray areas are shields covered by sedimentary rock. So, some examples: older Paleozoic era mountains are things like the Appalachians, which are deeply eroded. They're topographically less prominent. So if you compare like the Rockies and the Appalachians, the Rockies are much taller and spikier, while the Appalachians are shorter and more rounded because they're much more eroded because they're older. So the processes that produce a belt of mountains is called orogenesis, mountain generation. And so mountains that display faulted and folded rocks are compressional mountains, mountains created by compression. No, I stopped and restored. So, and the model for orogenosis is based off of plate tectonics. And Earth's major mountain ranges have all formed along various convergent mountain plate boundaries. So there are a few different types of mountain belting. The first type happens when there is subduction. So we're going to talk about Andean type mountain belts, which occur when an oceanic plate subducts under a continental plate. Also, when an oceanic plate subducts under an oceanic plate, you also get mountain belting. So when you have subduction, you get mountain belting. So the first type is the island arc type mountain belting. That's when oceanic plate subducts under another oceanic plate. So as oceanic lithosphere subducts, it causes melting and magma to rise up. And this causes volcanoes and various igneous rocks to form. So these island arc type mountain belts happen when you have it out in the ocean, forming islands rising up out of the ocean, like Japan, the Philippines, things like the Aleutians. This results from the steady subduction of oceanic lithosphere, and continued growth can result in the formation of parallel mountainous topography. These mountains tend to consist of igneous and metamorphic rocks, because there's a lot of heat involved. Now, Andean type mountain belting occurs when that subduction happens instead of under oceanic lithosphere, where it creates volcanic islands. It happens under continental lithosphere, where the magma rises up through continental crust. And this creates different situations. This is exemplified by the Andes Mountains, where there's a plate subducting underneath the South American plate. And it starts with a passive continental margin, which is a thick platform of shallow water sedimentary rocks. And eventually the forces that drive plate tectonics change direction, a subduction zone forms, and the oceanic lithosphere sinks under the continental lithosphere, melts, and rising magma helps create mountains. But because they're underneath a continent, you get more large intrusive bodies and less volcanic island building. So you start with the continental shelf and some continental lithosphere. You end up with the oceanic plate subducting. You get partial melting, rising. You get magma chambers that can cool. Some of these form volcanoes, but some of them just form large underground structures, plutons, that form the core of mountains like the Andes. And there's also some compression and folding, but a lot more structures built up by rising magma. So that's Andean type mountain building. So these are volcanic mountains that are primarily formed through a series of volcanic mountains are primarily formed through a series of volcanic eruptions. They're located along convergent boundaries, since that's where most volcanoes occur. Along oceanic convergent boundaries, you get chains of volcanic islands that form on the plate overlying the subduction zone. So things like the Aleutian Islands, Japan, the Lesser Antilles, these are all examples of volcanic mountains. Like all the volcanoes surrounding the Pacific. They also can form along continental oceanic convergent boundaries. The continental plate will always overlie the subduction zone, and this is where the volcanic mountains will form. The Andes Mountains in South America were formed as the oceanic Nazca plate was subducted beneath the continental South American plate. So you get these mountains that are volcanoes, but also underground igneous structures. And the Cascade Mountains are another example of this type of mountain. So up in Washington and Oregon. So here is an example of the Cascades in Washington. There are also, so that was Andean type mountains. There are also collisional type mountain belts. So Andean type mountains, volcanic mountains happen when an oceanic plate subducts under another plate. Collisional type mountains occur when two continental plates collide and are too thick and floaty to subduct. This is Cordellan type mountain building. And we can talk about, there's Cordellan type mountain building, which is associated with the Pacific Ocean. And is an indication the Pacific Ocean is unlikely to close. So subduction form zones can form island arcs that will eventually collide with continental crust. And like the west coast of the US is built up of layers of various things piling up. The collision and accretion of small slivers of continental crust from the mountain regions that rim the Pacific. This is Cordellan type mountain building. And you get these terrains, these crustal fragments of exotic material that make up much of the Western United States. So a lot of the Western United States is bits of various, island arcs, microcontinents and such that all spread away from the Pacific Ocean, slammed into the West Coast and piled up. That's Cordellan type mountain. So things like island arcs or microcontinents all sort of get glommed on and build up along the edge. So various small crustal fragments get glued onto a continental edge and build up and accrete up mountain ranges. So this is collisional, but it's not like the Himalayas or the Andes where two continents are colliding. So this is a short video about that process of the accretion of these small terrains, like we see along the West Coast.
Hi there, Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at terrain accretion. After watching the video, you should be able to describe what a terrain is, where it comes from, and how it gets added on to another landmass. If you look at the geological map for the western part of North America, whether you're looking at the United States or Canada or even Alaska, you will see that there are a bunch of different colored blocks of rock. And these blocks of rock are different terrains. Basically, they're chunks of rock that started off somewhere else and then they got added on to the western part of North America. You can see some of them have names of their own, but each of them basically is a distinct block of crust that is exotic to the continent that it's now part of. How do these terrains get there? Well, it looks something like this. Here's a situation where you've got the edge of a continent and a subduction zone, and at that subduction zone, oceanic lithosphere is being shoved down underneath the leading edge of the continent. You'll notice that the oceanic plate is not just oceanic crust, it's also got an inactive island arc and a microcontinent that are part of it. Let's see what happens as those land masses are brought closer to the edge of the continent. First, the island arc smashes into the edge of the continent. So those island arc rocks, probably basalts, maybe some andesite, maybe some limestone from the fringing coral reefs, that all gets smashed onto the edge of the continent, and the continent gains a little bit of mass. But now the subduction zone has been clogged up. So a new subduction zone will develop that's outboard or seaward of the old subduction zone. And now subduction begins anew. The microcontinent, something maybe like Madagascar or a Japan-sized object, that is brought closer to the trench, and it too collides with the edge of the continent. Now the continent has gained those microcontinent rocks along its leading edge. It's almost like bugs smashing onto the windshield of a moving vehicle. So these land masses end up basically starting off somewhere else and then getting smashed onto the edge of the continent in a process called accretion. Now here's the situation that existed off the east coast of North America around 600 million years ago. You'll see a couple of subduction zones there, and there's an island arc and a microcontinent with Africa on the far side of that. What do you predict is going to be in the future for these different land masses? Well, hopefully you said that they're going to be brought into collision, and that's exactly what happened. First, the island arc collided with the edge of North America, then the microcontinent collided with the edge of North America, and then Africa itself smashed in And then, of course, after Pangaea was formed, Africa pulled away. You can see here on the edge of North America that we've got some of these different exotic terrains. We've got these oceanic island arc rocks, we've got the microcontinent rocks, and we've even got little pieces of Africa that are left behind as terrains on the East Coast. Thanks very much for your attention. This has been another Smart Figure.
And the nature of these terrains, they're bits of other land that was out in between the continents. So some terrains were microcontinents like Madagascar, others were island arcs like Japan. But they all basically got scraped onto the continent and piled up. And this accretes. So small features of the ocean floor get subducted with the plate, but larger buoyant features don't subduct. They pile up on the edge of the continent, and you get accretion, but the whole thing is also being squished, so you get folding and mountain building as well. So the North American cordilla, so the many terrains that make up the North American cordilla were scattered through the Eastern Pacific, and during the breakup of Pangaea, the Farallon Plate began to subduct under North America, and this resulted in the piecemeal addition of various crustal fragments to the western side of the United States. As Pangaea broke up, various crustal fragments that were about in the Eastern Pacific accreted onto the edge of the US, and the whole continent got sort of squished and folded. So here are some terrains that have been added to Western North America during the past 200 million years. So these are areas that are folded and distorted because of the terrains, and then these various colors represent different terrains. So here is a short video about the formation of terrains.
Terrain formation. A terrain is a slice of lithosphere that has been added to the margin of a continent during the process of plate collision. Most terrains are accreted in association with an oceanic plate, continental plate subduction zone. Some terrains consist of slices of oceanic lithosphere, but in other cases, an entire island arc or volcanic seamount has been added to the edge of a continent. Here you see an ocean basin with a mid-ocean ridge spreading center and an active subduction zone with an island arc. As the pattern of subduction changes, the island arc becomes inactive and a new subduction zone forms along the continental margin. Now the old island arc moves with the oceanic plate toward the continental subduction zone. You also see a volcanic seamount form near the mid-ocean ridge. After forming, the seamount also moves with the oceanic plate toward the continental subduction zone. As the continental subduction zone develops, magma rises to form a chain of continental volcanoes. Slices of ocean floor and sediments accumulate above the subduction zone in an accretionary wedge. When the old island arc reaches the subduction zone, it is too buoyant to subduct, so it is added to the margin of the continent as a terrain. The subduction zone changes location to the new continental margin, so new intrusions of magma and volcanoes develop on the continental margin. When the old seamount reaches the subduction zone, it is also too buoyant to subduct, so it is added to the margin of the continent as a second terrain. The margins of many continents have grown through the accretion of terrains.
Now, fold mountains are mountains that are characterized by this prolific folding of the rock strata. So some examples of these are these compressional mountains where rocks get very folded. Some examples are the Alps, the Himalayas, the Appalachians. These are all examples of fold mountains. They're also characterized by thick packages of marine sediment. So the top of the tallest mountains in the world is covered with marine fossils. That's because it's the stuff that was in between the two pieces before they collided that got scraped up and piled up. It was originally deposited below sea level, and then it got uplifted and incorporated into the fold mountains. So marine fossils are regularly found high in a fold mountain range. So this is alpine type mountain building, is when you have the collision of continents. So the zone where two continents collide is called the suture, and it typically contains slivers of oceanic lithosphere that were scraped off the bottom as things formed. And most compressional mountains exhibit the deformation of a thick sequence of sedimentary rocks called a fold and thrust belt. First, the rocks fold, then as the pressure builds up, you start to get thrust faults. So here is a fold mountain in Alberta, Canada. You can actually see the layers folding. If you look here. The Himalayas are the youngest mountain range in the world, more or less, and formed by a collision. The collision began about 50 million years ago, where the Indian subcontinent collided with Asia, following the subduction of oceanic lithosphere. So that ocean that was in between India and Asia before they collided got scraped up, and it got pushed to the top of the Himalayas. So the Precambrian rocks of India resisted deformation, whereas the younger crustal fragments of Southeast Asia got highly deformed. And the whole thing is in fact still rising today. The Indian subcontinent is still heading north into Asia. It hasn't completely come to a stop. And it's raising the Himalayas and the Tibetan Plateau. So during the breakup of Pangaea, the subcontinent of India broke away from Africa, and as the Indian plate moved north towards Asia, very oceanic lithosphere was continually subducted beneath Eurasia. And during the time before the continental collision, sediments were deposited in the marine waters between India and Eurasia, because sediments happen. And that got scraped up and piled up on top of the Himalayas. So 80 million years ago, India was down here, it moved up, it made impact, 40, 50 million years ago, and collided with Eurasia, and has been piling up. And the sedimentary strata that was deposited between Eurasia and India eventually got uplifted and folded into the mountains. And when the continental portions finally collided, the subduction significantly slowed, because too thick continental crust, neither one could really subduct. And so what happened as they were moving, instead of one going under the other, they both folded and bent up. So the edge of the Eurasian plate got uplifted as the continental Indian plate wedged underneath it, and that formed the Tibetan Plateau. The Indian plate continues to move north today, resulting in continued uplift of the Himalayas. So there was ocean in between Eurasia and the Indian plate. Material got scraped off the bottom and uplifted and folded. So here is a video showing that process in detail, where there's folding and a bunch of thrust faults. Here's India, the Himalayas, and the Tibetan Plateau, which is higher up, as you can see. So here is sort of the process of a continental conversion, given the example of the Himalayas.
The Himalayas, the highest mountains on Earth, contain 10 of Earth's 14 mountain peaks that are higher than 8,000 meters, or 26,240 feet. The other 4 are found in the neighboring Karakoram Range. The Himalayas formed following the breakup of Pangaea. 200 million years ago, India was located in the southern hemisphere, wedged between Africa and Antarctica. About 145 million years ago, India began to separate from these landmasses. During the next 80 million years, India moved more than 6,000 kilometers to the north. The mountain-building episode that generated the Himalayas began as India collided with southern Asia between 50 and 30 million years ago. Because India is still moving northward, albeit at less than half its pre-collision rate, the Himalayas are still rising. India's collision with southern Asia is shown here using simplified cross-sectional diagrams. The driving force was the subduction of oceanic lithosphere along the leading edge of the Indian plate. As the dense oceanic lithosphere plunged into the mantle, it served as a giant anchor pulling the Indian landmass along. Continued subduction created a continental volcanic arc along the southern margin of Asia. Offshore, an accretionary wedge was created, consisting of deformed sediments scraped from the descending plate and the remnants of the seafloor. By contrast, India's northern margin was a passive continental margin, consisting of a thick platform of shallow water sediments and sedimentary rocks. During the closing of the intervening ocean basin, the more deformable materials on the seaward edges of these two landmasses became highly folded and faulted. In addition, two major thrust faults, and many smaller ones, sliced through the Indian crust. Subsequent motion along these faults caused slices of the Indian crust to be stacked one upon the other. Today, these slices make up the bulk of the Himalayas' highest peaks, many of which are capped by tropical marine limestones that formed along the continental shelf.
That's a sort of process involved. You scrape up what was in between them, and it all piles up in the middle. The Appalachians are of similar origin. They formed when Pangaea was forming. These are similar origin to the mountains of the British Isles, Scandinavia, Northwest Africa, and Greenland. They formed in three major orogenic events that accumulated with the formation of Pangaea. So, first, a volcanic arc located east of North America was thrust over the continental block around 450 million years ago. The volcanic rocks and marine sedimentary rocks were metamorphosed and are exposed in New York. Then the Akkadian orogeny occurred. The continued closing of the ocean basin resulted in a microcontinent colliding with North America about 350 million years ago. Thrust faults, metamorphism, and granite intrusions are associated with this event, and this substantially added to the width of North America. Yes, is there a question? No, okay. Thought I saw something in the corner of my eye. And this is sort of how the East Coast was built up. And then the Appalachians Alleghanian orogeny is when Africa collided with North America about 250 to 300 million years ago. Material was displaced about 250 kilometers inland on North America. And the Appalachians were formed. The final stage of the formation of the Appalachians occurred. Then Pangaea began rifting about 180 million years ago. The rift was east of the suture, so leaving behind a remnant of Africa welded to North America. So there's a little bit of Africa on the east coast of the US. And there's probably some people out there who would hate that fact. So there was this tectonic island arc, which merged with North America. In the tectonic orogeny, which is about 450 million years ago. Then the Akkadian orogeny, about 350 million years ago, where a microcontinent called Avalonia merged. And then lastly, there was the final closing of the ancestral Atlantic, where Africa collided with North America, forming the Alleghanian orogeny. And the remnants of this can be seen with the Appalachian Plateau, the Valian Ridge, the Blue Ridge, the Piedmont, and then the coastal plain. So here's a short video about the formation of the Appalachians.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the sequence of tectonic events that took place to produce the Appalachian Mountains in the eastern United States. The Appalachians are a very scenic place. It doesn't look like a mountain range like the Alps or the Himalayas. It's much more subdued than that. What ended up happening to produce the Appalachians were a series of tectonic collisions that took place during the Paleozoic era of geologic time. The Appalachians were actually built in 3 pulses of mountain building. Then they were eroded to grind them down to the present state of topography. Around 600 million years ago, off the shore of North America, there was an ocean basin, which some would call the ancestral Atlantic or the Iapetus Ocean. And in that ancestral Atlantic Ocean, there were various land masses, including a volcanic island arc and a microcontinent. On the far side of the ocean basin was the continent of Africa. Now, a subduction zone first brought the volcanic island arc into contact with the edge of North America. That collision took place around 450 million years ago, and it's called the tectonic orogeny. The next collision to take place was with the microcontinent, which is sometimes called Avalonia. Avalonia collided with the edge of North America around 350 million years ago in the second phase of Appalachian mountain building, the Acadian orogeny. But there was still some ocean basin left and Africa on the far side. As that ocean basin closed due to subduction, we ended up seeing the final phase of Appalachian mountain building, the Alleghenian orogeny. This took place starting around 300 million years ago, and it was pretty much wrapped up by around 250 million years ago. The moment that ancestral Atlantic Ocean was finally consumed was the moment that Pangaea was born. Notice now that there's continuous land all the way across this cross-section. Of course, something happened since then, and that's that Pangaea broke apart and the new Atlantic Ocean opened up. So Africa pulled away again, although Africa left behind a little scrap of its continental crust. That, for instance, underlies Florida. And then you can see these other exotic terrains of the microcontinent and also the ancestral Atlantic Ocean sediments and the volcanic island arc. Those have been smashed onto the edge of North America or accreted. And you can see that there was also a bunch of deformation that included a piece of the North American continental crust being shoved up and on top of its neighbors, and then the wrinkling of all the sedimentary layers that were west of that. So these are the different provinces of the Appalachian Mountain Belt that we see today: the Appalachian Plateau, the Valley and Ridge Province, the Blue Ridge Province, and the Piedmont. The coastal plain is the newest geologic province on eastern North America. It's basically a blanket of sediments that have been laid down since the Atlantic Ocean opened up. Let's zoom into Pennsylvania here. This is a classic view of the Susquehanna River cutting through the Appalachian Mountains of Pennsylvania. You can actually see several of these provinces right here in this picture. See if you can pick them out. All right, well, hopefully you identified the sinuous valleys and ridges that are so prominent in the central part of this picture as the Valley and Ridge Province, which in Pennsylvania they call the Ridge and Valley Province. To the west of that, basically everything over here in this region, that's the Appalachian Plateaus. Then you've got a little bit of the Blue Ridge Province, and then the Piedmont is to the southeast of that. Thanks very much for your attention. This has been another Smart Figure.
Another form of mountain building you can have is fault block mountains, where normal faulting, when the crust is stretching apart, can produce tilting and uplift of large crustal blocks. And you get these dramatic fault block mountains rising abruptly above the surrounding lowlands. Some examples are the Grand Tetons, the Sierra Nevada Mountains of California, and the Wasatch Range of Utah, all are examples of this. So here's Mount Whitney. So the crust can move vertically as well as horizontally. So the principle of isostasy is that basically the crust is floating on top of the mantle, the upper layer of the mantle. So the less dense crust floats on top of the denser rocks of the mantle, and that it's going to be in gravitational balance. So if you have a bigger block of crust, it will float, its bottom will end up deeper and its top will end up higher, because it's going to float buoyantly like any other object would float. So you can think about a series of different sized floating blocks on water as an example. And And if you add or remove weight from the crust will adjust. So if you suddenly took a weight off the top of the crust, it's gonna float up. Like if you had a block of wood in a pool of water with a weight on it, and you took the weight off, the block of wood will move upwards. So if weight is added or removed from the crust, you'll have isostatic adjustment. It will move up or down as the crust will subside or rebound. And that's happening in several places where the crust is rebounding from the removal of the weight of all the glaciers from the last glaciation period, the last ice age. Where there are these areas that were covered in glaciers, the glaciers retreated, there's now a whole lot less weight on them, so those areas are rising up. So crustal rebound is present in Canada's Hudson Bay region following the melting of the ice sheets over that region. So when you remove weight from an area, that area can rise up, float up. So here are these blocks, see how they're floating. And you can see how as you remove some weight from above or you wear away the top, the bottom will start lifting up. That's how you can get stuff that was once buried quite deep at the surface. Because as you remove the top, the lower layers will rise up because they're floating up. So here, if you took like a saw and cut the top off of a few of these blocks, they would float upwards because they have this deeper root, which would rise up. Just have. So here is a video about isostatic adjustment.
Did you know that Earth's crust moves vertically because of the addition or removal of weight? This movement is called isostatic adjustment, where the term isostatic means equal standing. A container ship floating on water provides a good example of how isostatic adjustment works. Notice how the empty container ship is floating high in the water near a dock. Press on the Load Containers button a few times to see how the ship adjusts to the addition of weight and floats lower in the water. Press on the Unload Containers button to see how the ship readjusts and floats higher in the water with the removal of weight. When you have finished loading and unloading containers, press the Continue Lesson button. As you have loaded and unloaded cargo onto a container ship, you have seen that the ship rides higher in the water when it is empty. You have also seen that the ship rides lower in the water when it is loaded with heavy cargo. To accommodate the additional weight of a fully loaded ship, water is displaced below. A container ship riding higher or lower in the water, depending on its weight, illustrates the principle of isostatic adjustment. Land masses also experience isostatic adjustment as weight is added or removed. For example, about 21,000 years ago, during the last ice age, northern land masses were covered by thick continental glaciers that made the continents ride lower because of the additional weight of the ice. At the end of the ice age, the ice melted and the land masses began to slowly rise back up, adjusting to the removal of weight. This process occurs slowly and continues in some northern areas even today. Both the continental and oceanic crust float on the mantle in a similar fashion to the way the container ship floats on water. Notice how the high-density oceanic crust rides lower on the mantle even though it is thin. Also notice that the thicker, lower-density continental crust rides higher above the mantle. Interestingly, what makes tall mountain ranges on land so high is that they have a thick root of continental crust below that keeps them buoyed up. Since continents slowly move up and down because of isostatic adjustment, it would make sense that they are also able to slowly drift horizontally from place to place across the globe. This is exactly what is happening on Earth today. The slow movement of Earth's plates across the globe, thanks to the processes of plate tectonics.
So one of the things that can happen with isostatic adjustment is you start with a mountain range with some stuff underneath, and then as the top gets worn away by erosion and weathering, the bottom rises up. And so you get things that were formed quite deep in the continental crust ending up on the surface. So this process of isostatic adjustment allows structures that were formed very deep underground to rise to the surface.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. In this video we're going to take a look at isostasy, and after watching the video you should be able to describe what isostasy is and how it affects landscapes. So let's take a look at a sequence of images here that describe the recent geomorphic history of California. And what you'll see is that we start off with the transition between continental lithosphere and oceanic lithosphere, and it's a passive continental margin, meaning that there's no tectonic boundary there. That changes when a subduction zone develops, and that subduction zone is responsible for a couple of different phenomena. First off, it generates magma, and that magma rises up through the crust to be erupted from volcanoes as a continental volcanic arc. And secondly, there is an oceanic trench that is scraping sediment off of the subducted slab that builds up into an accretionary wedge. Now, if you uplift that whole package, you'll notice that the accretionary wedge is now out of the water and it's a low range of coastal mountains, and the magma chambers that were at the roots of those volcanoes of the continental volcanic arc, those magma chambers are now at the surface. They're exposed as a batholith. You'll also notice that we've got a four-arc basin here, basically the zone between those two, where the strata are relatively undeformed. This is exactly what you see if you go through California from west to east. The low coastal ranges of mountains, California's Great Central Valley, and then the batholith of the Sierra Nevada. The principle of uplift is referred to as isostasy, and perhaps it's best visualized with the series of floating wooden blocks. You'll notice that because these blocks all have a constant density, that they end up basically floating at certain levels. Relatively short blocks, top to bottom, end up floating at a certain level with only so much poking out of the water, and then a root that goes down only so far. Whereas thicker blocks poke out more above water, and they also extend down more below water. In the same way, the continents and the thickness of crust in different parts of the continents end up having these thick roots below. And those thick roots are important. Imagine if I took a chainsaw and I cut off the top of this block right here, and I removed it. Now that block is going to weigh less, and it's going to want to pop upwards in compensation for that lesser weight. So that can actually happen in landscapes too. For instance, let's consider we've got a mountain range here at the top, and we got a photo here to match up with it on the right. You can see here that this is a relatively young mountain range, and it's just been shoved up into the air. It's got a fairly thick root down below it that protrudes down into the asthenosphere. And you can see that if we remove material off the top, it's going to mean that that mountain range weighs less. So that removal of material by erosion ends up facilitating the uplift of the range. What do you think the next sequence in this image is going to look like? What's going to fit in down here below? Well, hopefully you said continued erosion, and that the more material you remove, the less the crust weighs, so the more it pops up, the more isostatic rebound you see. And you can have a mountain belt that is completely non-mountainous, so it'll be completely flat, and the only way you'll know it is a mountain belt is by the structure of the rocks, metamorphic rocks and deformed rocks and granitic intrusions and things like that. Thanks very much for your attention. This has been another Smart Figure.
So, another aspect of it is that there's sort of a limit to the height of mountains. So as mountains grow, gravity will act on warm and weak rocks deep within the mountains, and eventually the gravitational forces are so large, the rocks will flow laterally, flow sideways. And this ductile spreading and consequential subsidence is called gravitational collapse. And it's one of the reasons why the highest mountain in the solar system is not on Earth. It's on Mars, where gravity is a bit weaker. So compression will cause shortening and thickening of the crust, but as time goes on, you can have collapse, where subsidence and pieces slide and stretch and thin the crust. So over time, eventually, gravitational forces can dominate. And that is it for chapter 7. So that's the end of chapter 7. We will start chapter 8. Chapter 8. Sorry about taking forever to save. Oh no. So, chapter 8, we're going to talk about, we talked about how mountains are built. Now let's talk about how they get worn down. Weathering, soil, and mass movement. We're going to talk about some of the ways that mountains get broken down. We'll continue that in chapter 9, which will talk about how water moves stuff. And because we're ahead of schedule, we'll probably also end up covering chapter 10, but it won't be on the test. Because we'll have extra time and just looking at where we're at, which will also talk about some of the other ways that stuff gets moved around. So let's start talking about weathering, soil, and mass movement. This is how stuff gets broken down, how soil forms, and mass movement, the movement of stuff down soil. So we'll talk about 3 types of external processes and discuss the role each plays in the rock cycle. We'll define weathering and distinguish between the 2 main categories of weathering and summarize the factors that influence the type and rate of rock weathering. We'll define what soil is and explain why soil is referred to as an interface. We'll list and briefly discuss the 5 factors that control soil formation. We'll describe an idealized soil profile and explain the need for classifying soil, which gets very detailed because it gets important in things like agriculture. But we'll describe the detrimental impact of human activities on soil and some ways that soil erosion gets controlled. We'll discuss the role that mass movements play in the development of landscapes. We'll summarize the factors that control and trigger mass movement processes. And we'll list and explain the criteria that are commonly used to classify mass movement processes and distinguish among 6 different types of mass movement. So mass movement is material moving downhill under the influence of gravity without some other medium moving it. So it's not like being carried away by water or wind. It's sliding down a hillside. So let's talk about Earth's external processes. There are 3 main types. There's weathering. Weathering is the breakdown of rock into smaller pieces. The disintegration and decomposition of material at or near the surface of the Earth. So this is, changing rock from big giant boulder into smaller pieces. Mass wasting is the transfer of ground material downslope under the influence of gravity. This is stuff slides down the hillside in some way. There are both fast, violent mass wasting and slow, gradual mass wasting. And then there is erosion, which is the incorporation and transportation of material by some mobile agent, usually water, wind, or ice. So the most common source of erosion is water. Water is the biggest carrier of material around, followed by wind and ice. So glaciers can carry material and the wind can carry material, but streams carry a whole lot more material. So weathering is this process of either where environmental agents cause the physical disintegration, the breaking up of a thing into smaller pieces, and or the chemical decomposition, so the chemical breakdown of a rock, of rocks and minerals at or near the Earth's surface. So this is what weathering is. So weathering is the process of a rock being broken down into either smaller physical pieces, so you could weather a rock by hitting it with a hammer. That would be physical disintegration. Or you could weather a rock by pouring acid on it, causing it to dissolve. That would be chemical decomposition. And weathering is generally a slow but powerful force that will eventually break down even the most resistant materials. We live in an environment with plentiful weathering, which is why there's so many potholes. The processes that weather rock also weather our roads and generate things like potholes. So the rock mineral types, so what rock is around, the amount of moisture available, the temperature, and the overall climate largely determine the rate of weathering. So for example, we have pretty rapid weathering around here because we have a reasonable amount of moisture and we have temperatures that regularly pass back and forth between freezing and not freezing. And that drives one of the major processes of physical decomposition, which is frost wedging. So weathering can be divided into two categories: mechanical weathering, the breaking of rocks into smaller pieces, and chemical weathering, the chemical transformation of rock into one or more new compounds. So mechanical weathering is a physical disintegration. It's some process that breaks rock into smaller bits. And chemical weathering is a chemical process. There's some chemical interaction, usually with some sort of acid, that interacts with the rock and things dissolve or new compounds form. So some examples of mechanical weathering. One of the biggest forces of mechanical weathering around here is frost wedging. When water freezes, it expands. If you'd like to experience frost wedging yourself, fill a bottle up with water to the top and freeze it and watch it break. And so freezing water expands, it gets bigger. So when water freezes in a crack in the rock, it wedges it apart. And if it then melts and refreezes, it wedges it apart more. So places with rapidly cycling between freezing and not freezing, like here, get dramatic cases of this frost wedging, where freezes, melts, moves down deeper into the crack, freezes, melts, steadily making the crack bigger. Another effect is sheeting, which is when rocks are exposed at the Earth's surface and suddenly are under a lot less pressure, they expand. And this can actually cause them to separate like an onion in layers and form sheets. And so you get the exfoliation of rocks at the Earth's surface as a result of a reduction in confining pressure. You can have a similar effect to frost wedging with the growth of salt crystals, where salt crystals form in cracks and enlarge the crevices. This tends to happen in places with more salt, warmer environments than frost wedging. And then there's biological activity. You get disintegration resulting from plants and animals. Things burrow through the ground, roots grow in cracks, wedge them open, things like that. So, but one of the biggest factors is frost wedging. Ice breaks rocks apart. So water gets into cracks, expands as it freezes, and makes those cracks bigger. So ice wedging or frost wedging is this process.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at ice wedging. And after watching the video, you should be able to describe what ice wedging is, why it happens, and its effect on rocks. So let's begin our discussion with this iconic landmark. This is the Old Man in the Mountain. It's in New Hampshire, or I should say it was in New Hampshire. This sort of craggy looking face over here. So the idea is that this looks like a face to some people. That face basically broke off and dropped off the mountain at some point in recent history. And because it dropped off the mountain, New Hampshire lost a vital symbol, but we can take advantage of this because this offers a great lesson in geology. So the basic idea here is the idea of ice wedging. The way ice wedging works is that water expands in volume by 9% when it turns from water into ice. So 9% increase in volume means that the ice basically pushes outward on any sort of container that it's housed in, and that can cause that container to break. So here's a non-geological example, a bottle shattering when the water inside freezes. And you may have experienced this yourself if you ever put a bottle of some beverage into the freezer and then it froze before you had a chance to drink it. Well, the same thing applies to rocks. So high up in the mountains, water gets into little fractures in the rocks. As that water freezes, it pushes outward on those fractures, so it basically enlarges the volume of the fracture, and that can actually serve to make the fracture propagate, so the little tip of the fracture will propagate out and the fracture will get longer, but it will also widen the fracture, and that can cause blocks of rock to go tumbling over the edge. So this happening every winter, tumbling blocks of rock down, you can see that this big giant pile of rock has built up at the base of the mountain. So here's the source for those sediments up here on the mountain cliff, but they end up piling up down below on what's called a talus slope. So this talus slope it's made out of boulders that are derived from the cliffs up above it. Now, can that same principle be applied to anything besides ice? Hopefully, the picture here prompted you to say yes. Obviously, tree roots can also penetrate into fractures in rock. And as those tree roots grow, it's not the same as freezing, but they end up basically exerting an outward pressure on that fracture, and that can cause blocks of rock, like this one here, to be popped off the face of that cliff. So root wedging works in much the same way as ice wedging. Both are vital forms of physical weathering. So where does that leave us with the Old Man in the Mountain? Well, that craggy profile that we looked at earlier is actually a function of ice wedging, and the breakdown of that profile was also a function of ice wedging. This was a feature that was both created and destroyed by the same process, ice wedging. Thank you so much for your attention. This has been another Smart Figure.
So this mechanical or physical weathering is the breakdown of rocks and minerals into smaller pieces, disintegration without changing the chemical composition. And frost wedging is a specific physical weathering process caused by the expansion of freezing water and fractures, joints or cracks in rock outcrops, because water increases in volume about 9% during the freezing process, and the force expands the fractures and loosens the fragments of the rock. And I think this is actually McDuffin. Well, we could. Don't remember it.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away. When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
So here's some more examples of things created by frost wedging. See this sort of jagged fragmented structures where these got torn apart. Now, when you have something like a dome of material that was formed under pressure, and it gets exposed, and that confining pressure is removed, it expands. And this can actually cause cracks sort of parallel to the surface. Basically, it starts to flake off and peel. And this is called sheeting. So here is a short video about the process of sheeting.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the phenomenon of sheeting and discover how it forms and what its consequences are. So let's begin our discussion by taking a look at the iconic landmark called Half Dome. This is in Yosemite National Park in California. Basically, there's two things at work here. First off, let's note the scale. There are people here climbing a ladder to give us a sense of scale. Part of Half Dome, basically everything to the right of that line, has been removed by glacial action. And we'll talk about that perhaps in the glacier chapter. However, what we want to focus on right now is this sort of onion skin looking feature here, these flakes that seem to be coming off, and they're all parallel to the sides of this dome, or half a dome. So what's going on here is that Half Dome is made out of granite. Granite, as you know, is an intrusive igneous rock and forms deep underground, so it forms under confining pressure. So there's basically pressure on that magma chamber at the time it intrudes into the crust, and then it crystallizes into igneous rock. So crystals form and it becomes one of these big blobs of igneous rock that we call a pluton. Now, if later on that pluton is brought up to the surface of the Earth, the pressure on it has been released. And as a result of that pressure being released, it actually expands outwards in all directions. So the relief of the pressure basically causes it to increase in volume very slightly. And that increase in volume is actually greater than the strength of the rock. And so the rock tends to break in a series of fractures that are basically perpendicular to the expansion direction. So if it's expanding in all directions, you end up getting this onion skin-like pattern of flakiness on the outside of that pluton. So when you go to Yosemite National Park, you're going to see this just about everywhere you look. You might hike up to view a waterfall, but look beyond the waterfall and you can see all these parallel fractures of rock. These are examples of sheeting. All right, let's quiz you real quick. Which of these two types of rock, intrusive igneous rocks or extrusive igneous rocks, are going to be most likely to experience sheeting when they're exposed at the surface? Hopefully you said the intrusive igneous rocks because they form deep underground under confining pressure. The extrusive igneous rocks wouldn't work because they form at the Earth's surface, so there's no reason for them to expand when they're exposed at the Earth's surface. It's only the intrusive igneous rocks that basically form at depth and then will expand when they're brought to the surface. So an example of an intrusive igneous rock would be a granite. Thank you very much for your attention. This has been another Smart Figure.
So another form of surface that undergoes mechanical weathering is permafrost. So permafrost is this permanently frozen state of soil profiles in cold, higher latitude areas. And during the short summer season, the top layer of the permafrost can melt. They thaw, and then you get this wet, spongy conditions, and you get these sort of flow down hills and such, and these weird ripply surfaces. And this contributes to the physical water weathering process, and it's also promoted in a small way by the action of burrowing animals. Physical weathering is also promoted by burrowing animals and by plant roots that grow into and expand rock crevices. So we can see this where living things cause weathering. So this is a video about various forms of weathering caused by living things. So there's both physical and chemical weathering in this video.
So looking around us here, this is an excellent example of just how weathering happens, whether through biological or other physical means. So we don't have a lot of, well, there may be a little bit of chemical weathering going on here with rainwater and stuff, but this is some fairly stable sandstone. So we got little sandstone surfaces in here still visible, but we were just marveling at how thick and dense the moss is along the side of this cliff. Okay, you can see as I push into it just how plush it is, which means that we've got generations and generations of moss that's been growing, finding every little tiny nook and cranny in that rock and forcing those cracks just a little bit wider. Eventually yellow birch seeds are able to fall onto the moss, take purchase in the moss itself, and then work its way into any cracks that happen to be wide enough in the rock. Like this tree is on there. I could probably climb that sucker, and it's only about the diameter of my leg. Then eventually, as those cracks widen open, we get rocks that are falling off here, big cracks in between the rocks here, and then entire canyons that I could literally walk into here, that form between the rocks as frost wedging speeds things along and other processes encourage, as my pack gets stuck on the rock, as other processes encourage that kind of breaking open and weathering of the rock, all in place, in situ as we say, and eventually gravity will take hold and knock big chunks of those rocks off, and then other processes of erosion can get involved as well. But in the meantime, this is a great nursery of mechanical and biological weathering.
Now, that's physical weathering. There's also chemical weathering. Chemical weathering alters the internal structure of materials by reacting with them chemically. So removing or adding elements. And the most important agent of chemical weathering is water. Because water is incredibly good at dissolving stuff. It's one of the best things at dissolving stuff there is. It's good at moving stuff around. It's also good at having things dissolved in it that help cause other processes. So for example, oxygen dissolved in water will oxidize materials. For example, rust. Rust is oxidized iron. And rust does not stick around with the iron. It flakes away, so that effectively weathers the iron. Carbon dioxide dissolved in water forms carbonic acid, and that makes the water slightly acidic, which can allow it to dissolve things like limestone, calcite. So chemical weathering changes the chemical composition of rocks and minerals, principally through reactions with water. The two main factors that drive the rate of chemical weathering are water and temperature. Water is usually required for most of these processes for chemical weathering, and chemical reactions happen faster when it's warmer. Pretty much all chemical reactions are faster when it's warmer. So in hot, moist tropical environments, chemical weathering is most efficient. And you get some really dramatic things like those in Southeast Asia. They have these crazy pillars that have been weathered away by various processes. And limestone, which is a common rock at the surface, readily undergoes chemical weathering. So you can get really dramatic things as limestone dissolves. You get these giant cave structures. So caves get formed by the dissolving of limestone, things like that. Now, one of the things that happens is feldspar minerals in granite, potassium feldspar minerals will weather chemically to produce clay minerals. A soluble salt, potassium bicarbonate, and silica in solution. While quartz remains substantially unaltered. So what you get is you'll have like a chunk of feldspar, like a chunk of granite. The feldspar will turn to clay. The small quartz crystals will remain as sand, basically. And other silicate minerals will produce things like iron oxides and clay minerals. So quartz grains will remain as quartz grains, as sand. The material in solution is silica. Feldspars will form clay minerals with some silica, potassium, and sodium and calcium in solution. Amphibole will form clay minerals and iron oxides with some silica, calcium, and magnesium in solution. And olivine forms iron oxides with silica, magnesium, and such. So there's various things that form from this oxidation, these oxides, that require water to form. Additionally, one of the things that can happen with chemical weathering is it can turn things rounder. It will attack corners more than flat surfaces effectively. Because it works inward from the exposed surfaces. So it will be doubly affected at an edge and triply effective at a point, effectively. So, and that will steadily round away rocks. So water will work its way from the edges. It'll attack the edge on both sides, a corner on 3 sides. That will round these things off. And eventually you'll get spheroidal structures formed just for chemical weathering, as you can see here as an example. That's in Joshua Tree National Park in California. Another effect is that limestone is affected heavily by chemical weathering. It's made up largely of the mineral calcite. Normal rainwater reacts with carbon dioxide in the atmosphere to form a weak solution of carbonic acid. And the more CO2 the water comes in contact with it, the more carbonic acid is formed. And as water percolates through soil, it can react with even more carbon dioxide released by various bacteria living in the soil and other things. And it becomes acidic. And limestone reacts with acids and dissolves in acids. So one of the ways you can identify calcite is by putting an acid on it. So usually dilute hydrochloric acid is used, and it'll bubble up because the process releases carbon dioxide. So as carbonic acid comes in contact with the calcite in limestone, they react to form CaHCO3, calcium bicarbonate, which readily dissolves in water and gets carried away in solution. And most chemical weathering in limestone occurs along fractures where the most water flows. And this, over time, forms underground caverns. And the cavern ceilings can collapse, causing sinkholes. And that's about all we have time for today. So I'm going to stop there.